All right, natural log is a log function. It is the inverse of the exponential function. So what does inverse mean? Come on, y'all, please. Okay, so opposite is very close. The x and the y switch on inverse functions. So if you think about whenever we did that exponential function, it kind of looked like, and actually not kind of, but it looked like this. If you turn that around on its side to do this, that's what the natural log function is going to look like. Okay, so it has an asymptote, but this time instead of a horizontal asymptote, it has a vertical asymptote. This one is 0. That's my vertical asymptote. Remember, we only have 3 to get through today. Yay. When you do your t-chart, x is never going to go negative because my asymptote's bounding it. It's going to be on the right side of the asymptote. Okay, so let's do 1, 2, and 3. You have a natural log button on your calculator. If you take your calculator, right here's third one up from the left, natural log of, and remember there's that asymptote at 0. If I put 0, you'll notice I get an error. It won't let me do it, okay? So it's kind of a double check for you on your calculator. But let's do natural log of 1, and I get 0. Natural log of 2. Does anybody remember what natural log is? It's a log with a base of something, a special base. Natural log is the same thing as log base e. That e we did yesterday. All right, and then natural log 3, 1.10. And so let's graph them. 1, 0, 2, 0.693, and 3, 1.1. And it does just like this. Is that continuous? Yes, it is continuous. How about the end behavior? To positive infinity, so the right side, what does the graph do? Right side, infinity. Now the other side is a little bit different because x doesn't go to negative infinity. But x is getting closer and closer to something, what? 0. So as x gets close to 0, what does the graph do? It goes down really fast, right? The closer you come over here to 0, the further down the graph is. So y goes to negative infinity. So it looks a little bit different than what you're used to seeing, and that's just because that graph is on its side. It's the inverse of what you're used to seeing. How about the domain? Close. You were closer the first time. What's the smallest x can be? Or what bounds x left to right? 0 to infinity. You said infinity to 0. You're really close. How about the range? Negative infinity to infinity. Is it bounded? No, it's not bounded. Forever up and down. Is it symmetric? Does it show any type of symmetry? No. It doesn't go past that y-axis, so it can't show any type of symmetry here. So no symmetry. It's neither. It's neither. I think that's it for that one. Any questions about that one? Pretty fast. The next one won't be. The next 2. Here goes the next one. The next one I'm really going to have to talk to you about because it's going to be a little bit harder to understand. I'm going to guess that this is something you have never seen before. This is called the greatest integer function. Yes.
Alright, so for my homework, I put the same numbers in the chart like you did for the work in class, I think.
Mm-hmm.
So can I just follow you with the homework?
You can if you want to.
I'm gonna write in my book for you.
All right. Here's what greatest integer function does. Whatever you plug in here, okay, it spits out the closest integer that is smaller. Let me think. A half goes to 1. 1.5 would go back to 1. Yeah. Okay. It rounds it down. In other words, if you plugged in 1.5, it would give you 1. It rounds it to the nearest integer below it. Does that make sense? Yeah. So, it'd be, right. And so here, what we're going to do, we're going to pick some values here. We'll do 0. We're going to pick some values that are, I'm not going to say 3 over 2, I'm going to say 1.5 so you can see. And then you'll be able to pick up the pattern. All right, so at 0, if I plug in 0, I'm going to get 0. Okay? If I plug in a half, I'm going to get 0. Now if I plug in 1, I'm going to get 1. If I plug in 1.5, you get 1. If I plug in 2, 2. If it's already an integer, it stays that value. Okay? But the minute it goes over, it starts shooting it back down. Okay? So I want you to think about this for just a minute. Here's 1 and 2 and 3. Zero, 0 is a point, right? 1/2 0 is a point. And in fact, all of these values here would still be 0, right? 1/2, 3/4, 9/10. They're all going to round down to 0, right? All the way until I hit 1. And when I hit 1, it jumps up and becomes 1, right? So what I'm going to do is I'm going to take this line all the way to 1, but I'm going to put an open circle at 1 to say, don't include 1 in this line. But all these little fractions in between 0 and 1, I'm going to keep them on this line. Now I'm going to do the same thing when I get here. 1.5 is going to be 1, right? And in fact, all of these values up until I get to 2 are going to be 1 because it doesn't switch and jump to 2 until I actually get to 2. Again, I'm going to put an open dot to say, hey, when it hits 2, it's not 1 anymore, it becomes 2. Do you see the pattern here and how this is going? This is sometimes called a step function. And the reason is it really looks like steps. Okay, it goes off the other way as well. This to me is the hardest one to grasp. Does that make sense though, what we're doing? Okay. No? Okay, I thought you said no. Let's see. Is this continuous? No, we finally hit one that is not continuous. What type of discontinuity does it have? A jump. You're absolutely right. It jumps. It's a jump discontinuity. Good job. I'm going, I stop and go, and I jump up to another piece. And then I go, and then I jump up to another piece. So it's a jump discontinuity. Y'all good on that? How about, and this one we're going to have to write a little bit differently too. How about the domain? Well, actually, domain we want to write different, but range we will. I can plug anything in, right? I can plug any x value in. It's what it spits out that's really different. What does my range look like? What all can y be? If you say negative infinity to positive infinity, then you're including all of these in between numbers. So can y be a half? I can never spit out anything but whole numbers here. That's what the function is doing. So what is the range? It could be 0 zeros in it. What else? What else? What are you doing? But what are you doing when you give me those numbers? 0, 1, 2. Counting. Counting what kind of numbers? Whole numbers. If I include the negative numbers, then they're not whole numbers anymore. They're called integers. All real integers. Okay, if you want to write it like that. If you want to write it in set notation, you can. -1, 0, 1, 2, ... Or if you just want to write all real integers, that's fine too. Everybody okay? How about the end behavior? As x gets bigger, what does y do? It jumps up, but it's still doing what? Is it still getting bigger? It's still going to positive infinity. How about negative infinity on x? As I move further left, it's still going down. It's just going to be an integer, but it's still an infinite integer. All right, last one. Y'all ready for it? Oh, I'm sorry. I left symmetry off of your sheet. Does it show symmetry? It looks like odd symmetry to me. Right? Would reflect over that line? Yes. Odd. Last one. Yay! Y'all excited? It'll look just like this. Mm-hmm. 12. This is 12. All right, yeah. Record again. This is what we call the logistic function. I think you'll see whenever you see the equation. It's that spider. He's got me. It's probably an email. All right, asymptotes. There are two. They're both horizontal. Y equals 0 and y equals 1. We're going to be scrunched between two asymptotes. It'll be fun. Such fun. So 0 and 1. We need to get on both sides of the axis a little bit. So let's do -1, 0, and 1. Definitely use your calculator for this one. When you do, make sure this is in parentheses. When I do 1, or -1, let's do -1 first. 1 divided by, put this in parentheses, 1 plus second ln. Now, there's already a negative there. So if there's already a negative there, and I'm plugging in -1, yeah, see, this original one has a negative already. So if I'm doing e to the negative and then I plug in -1, that becomes what? +1. So really this is to the first power. Close those parentheses off and I get 0.2689. So I'll say 269. If it's easier for you to put it in y equals and go to your table, then do that. That's fine too. Then 0, if you hit second enter, it'll pull up what you've already typed in, and you can just go right in and change it. 1/2. And finally 1, but it's going to be -1 because remember that negative in front. 0.731. Just nothing goes negative. If you look at those two asymptotes, I'm scrunched between 0 and 1. So all my values, all my y's should be positive, and they should be between 0 and 1. All right. This is 0.5. So I got -1, 0.269. So about halfway to a half. 0 1/2. And 1.731. And so this is what it looks like. It's kind of like a stretched out S. Probably looks a little better. Let me show you on my calculator what it looks like. 1 divided by 1 plus e to the -x. Let me adjust my window. I forget I have to do that. Window, come on. I'm going to set my y between 0 and 1 so the asymptotes are keeping it. Let's see how it kind of stretches out there that way. Now I'm taking this one, my x is going all the way out to 10 and -10. That's why it's kind of... But anyway, you can play around with that window. Looking a little closer to mine now. Okay, that's the logistic function. Is it continuous? Yes. What's the domain? Come on, y'all can do this. Yes. How about the range? 0 to 1. 0 to 1. Is it symmetric? Nope. If it had slid down some, then yes, it would be. But because it didn't, it's neither. Is it bounded? Mm-hmm. Above and below, right? Those asymptotes are bounding it. Oh, yes, in behavior. Thank you. I knew I was missing one. As x goes to infinity, what does the graph go to? Does it? 1. The right side comes closer and closer to 1. How about the left side? 0. Tell me what you think. That's all 12.